Recently, we reviewed the fact that two binomials, those are these things with two things inside, aka binomial, when multiplied, create an expression that has an x squared term in the front, especially if you have an x multiplying an x. And that's the typical way you're going to see it, although we might mix it up and put some numbers in front of them as well. Now, because it creates an x squared term, this would also be a quadratic equation and would graph as a parabola. So, we have an entire type of equation format that we call factored form that is based off of this idea of multiplying binomials. And the generic version looks like this. R1 and R2 are a special idea called roots. And roots are extremely important in quadratics because roots are at the heart of real-world applications for this type of equation. Unlike a lot of other things, which really in real life don't conform to the math, quadratics actually is based off of a lot of really interesting things like gravity. Gravity follows a very quadratic pattern. So if you toss something and you were watching it in slow motion, you would see that it creates a parabola. You can kind of think about that. If I toss a ball, it almost seems like it slows down towards the top, and then it has that turning point before it comes back down. And if I toss to somebody else, it creates an arc in the air. I can't just send it straight forward. I have to arch it up a little bit so that it'll go the distance. Well, roots in a lot of applications are based off of like the ground. And on the graph, they're going to be these x-intercepts. Now, if my parabola went the other direction like that, then you can picture that this would be the ground, and then it goes up and over, and then hits the ground again. So roots are very important, and in factored form, they are extremely easy to find because the numbers are right in the equation. We don't have to figure them out, we don't have to think about it. We just have to remember some very important information, which is that the minus is part of the equation. So, a reminder, our special thing that we're trying to remember is that anything in parentheses is the opposite sign that it appears to be. So, if I see x minus 2, like in our example, the root is actually positive 2. Same with plus 4, the root is actually at negative 4. And remember, these are the x-intercepts. So not like y equals mx plus b, which was the y-intercept, but same idea, just on the x-axis. Now, it's not quite enough to know where the roots are if we wanted to actually graph this. We'd have to do a few more steps. The cool thing about parabolas is that they are symmetric on both sides. So the line of symmetry is something we can easily find if we know the roots. The line of symmetry, you're going to take the two roots, add them together, and just divide by 2. We're averaging those two things to find what number is exactly in the middle. In this case, it was negative 1. And you can draw a vertical line there at x equals negative 1. And that will perfectly divide the parabola in half. We'd have to take it one step further if we wanted to actually plot this onto a graph by plugging that x value back into the equation. That last step will give us the y value, or the y coordinate. So here I'm literally just taking x equals negative 1, which was my line of symmetry, and I'm plugging it into the original equation, which was x minus 2, x times x plus 4. And I get negative 9, and you can see the vertex is right there at negative 1, negative 9. If it helps, you can also think about that stretch factor, which is part of the general form. It could be 1, like here. There's no number in front of the two parentheses, but it could be a different number. And we'll worry about multiplying that out in the future, but the stretch factor works the same as in the other formats of quadratic equations. So you can think about over 1, up 1, over 2, up 4, if it's just 1, or modifying that by multiplying. See you in class.